Hello, Liz. Good to see you.
Good to see you too.
Yeah, I was worried that you might
I
have
know
forgotten.
no, it's a little late for us, but it's fine.
All right. I can see Ivan also is there. Hello, Ivan.
Yes.
Hey there.
Great. So let's give it another minute or so. So hope you guys are doing well.
Yeah.
How's
As
the
good as one
weather?
could expect.
Yeah. How's the weather in New York?
It's been actually really nice, oddly enough. Like very strange for November.
Now here in Vancouver, it's cold and rainy.
No, sorry.
All right. Sorry for keeping you being like
No
that
problem.
late.
That's fine. We're happy to be here.
Great. Now let's give it 30 more seconds and then we're right on time to start. Slowly, students will come from another class to this one. It's now with all these online classes, it's easier for students to jump from one class to another.
It's true.
Like here on UBC, we have a very large campus, and sometimes the gaps between classes is only 10 minutes. You see all the students are like rushing to the next class.
Now, is everybody remote at this stage or some sort of hybrid?
No, nothing. Yeah, it's all online. All the lectures are online. Everything is online. And
do you know about next semester yet or not yet?
It's going to be online as well.
Okay.
Next semester is online. Summer, we are not sure yet, but we are hoping we return back in person.
Yeah.
All right, maybe it's time. So just let me quickly introduce you, or I let you to introduce yourself. So hello everybody in MAC 392. Welcome to another lectures. Today we are excited to have Liz and Ivan from NTop. And myself, I'm also excited about today's lecture. They're gonna talk about a very cool software, Ntopology, and all the cool stuff that last lecture we talked about, which is not possible to do with regular manufacturing. And now with additive manufacturing, you can have all these gyro and all these complex shape. And then we said that we need a tool to make all these. Here is the tool, is the NTop. So I'm gonna stop here and let you guys to introduce yourself, and the rest 1 hour of the class is yours. Go ahead, please.
Okay. I'll go quickly. I'm Liz Aram, the Education Partner Manager at Ntopology. So if you have any questions or if you need a license, I'm the person to contact, and I will put that in the chat right now. So those are both my email, and if you wanted the academic license, just click on that link and fill out a form, and I can, within a day or two. And there's lots of resources to get up and running. I'm gonna hand it over to Evan, who's gonna show you all the wonders of NTop.
All right, I'm going to start sharing my screen. Liz, can you just give me a thumbs up when you can see it? The old usual, thank you, appreciate it. I'm gonna make sure I have chat open and all that. And what I wanna say is I have a few things that I'm here to talk to you about, right? But this works, this is getting on the larger side, so if you have a question, put it in chat and I will do my best to answer it. But this is gonna be as much of a conversation as possible as opposed to a presentation, but we are getting on the higher side of attendees, so chat would be best in this instance. But my name is Evan Pills. I'm an application engineer here at Ntopology. That means I use the software 8 to 10 hours a day. I'm working with customers, creating new applications, and I'm excited to be talking to you today. I want to start off with about 10 minutes or so of slides, and then I'm actually going to just spend the rest of our time in the software showing you different applications and ways you can use it. So we are Ntopology, that's our company. We were founded back in 2015, and we started off with a software called Element Pro. And Element Pro was solely a latticing software, so it was very good at doing complex latticing, but it didn't do anything else besides that. So towards the end of 2016, we started developing this NTop platform, and that's the software I'm here to talk to you about today. And in 2018, we released the beta, and we received a $3 million investment from Lockheed Martin, and they were one of our main customers / testers in the early phases of NTop platform. Fast forward to 2019, we launched NTop platform publicly, and we had our Series B fundraising round of $20 million. But we also got Carl Bass to join our board of directors, who is the ex-CEO of Autodesk. So that's a pretty neat person to have on your board. And here in 2020, we've had an interesting year, as everybody has, but we've been releasing NTop platform toolkits, which are pre-packaged workflows. And we also had our Series C fundraising round, and we were given a $40 million investment. So why am I telling you about all this money we make? It's to say, why do people have an interest in NTop platform? Why are people using it? And we can boil it down to three main reasons. The first being our implicit modeling technology that we use. So as opposed to your traditional BREP tool, which means boundary representation, we model with implicit geometries, which gives us a lot of ability for complexity. Now, combining this implicit modeling with a field-driven design approach allows us to unify things like simulation and design. So now your stress analysis can be used to modify your geometry. And third is this idea of reusable workflows. So every workflow you create in NTop platform is totally reusable from beginning to end. And I'll show that to you in just a minute, but that can save you a lot of time with design iterations, designs of experiments, lots of different things. And this really is a new approach to modeling. So if anybody here has any additive manufacturing experience at all, what you'll have seen before is one of these error screens at some point in time, right? So your traditional tools, your legacy tools, the ones you're using today, were not built with additive manufacturing in mind. So when you start doing crazy things like incredibly complex lattices, like this image here on my right, you start to run into these errors that you can see down here on the bottom right, in the middle. And NTop's goal is to try and eliminate as many of these errors as possible, because once you see these errors, it means you have hours on hours of work to attempt to fix them normally. So because I said, NTop's goal is to remedy those issues, we still can't expect everybody to only ever use implicit modeling, so we work with a whole lot of different data types. You can see your CAD surfaces here that you can import into NTop, simulation, volume meshes, surface meshes, point clouds, slices, just a ton of different data types that you can work with inside of NTop platform. And you'll see this CAD surfaces here, you still have those faces, edges, and points that are indicative of a boundary representation. But an NTop model, which is an implicit model over here on my right, you can see that it's the exact same geometry, but you don't have any faces, edges, or points. That's because it's not a boundary representation, it's actually a volumetric representation. And that is what lets us do these incredibly complex things very easily and very quickly. So what does that kind of look like on the back end, right? I can tell you we can do these things, but how does it happen, right? What's the magic? Well, on the left here, you can see a very simple representation in your legacy tool, and the equations needed to represent that patchwork of faces that it uses to represent your geometry. Pretty simplistic. As well as over here in our NTop model, our implicit representation, we have a very simple equation as well. But when we do something a little bit more complex, like merging two cylinders together and blending between them maybe, the equations needed to represent those CAD surfaces get very complicated very quickly, but the implicit equation that we use is still very simple, and therefore we can do these complex things much easier and much quicker. So let's take a look at an example workflow, right? I kind of gave you some background, how it works. Let's see something that was actually done here. And what I want to do is take this robot arm I have, and the blue body, right, this blue portion, I want to do some topology optimization, meaning I want to lightweight this part by as much as possible through a smart process. It's going to put the material where it needs it. And what that process looks like is I'm going to start off in my CAD tool, right? This part here, it should be designed in CAD. Everything about it says design this part in CAD. We're not here to replace your CAD tools. We're here to complement them and to work with them. So we're going to start out in our CAD tool. We're going to bring this CAD into NTop platform and do a topology optimization process. And we're going to end up with this result And this is where the hard work really starts with these complex geometries. We need to do a lot of post-processing, smoothing, replacing features and faces and all that sort of stuff. We're going to do all of that work inside of NTop platform. And eventually, because this is a top-up part, we're able to convert it back to CAD geometry here. Then we're going to go back into our CAD part, do a final CAD Boolean. So we're going to get these nice prismatic faces. That lets us put reference points for our post-process machining and make an engineering drawing. And here's a nice little flow chart that kind of helps bring this all together. We're going to start over here in our CAD system. We're going to go into NTop, do the complicated work, come back to the CAD tool, do our final little bit of work. We're going to make our engineering drawing, and we're going to put it in the assembly. And this is a very general workflow, but here's a little video of the part actually in SolidWorks, right? I'm not lying to you guys. We did create this part. We did bring it back to SolidWorks, and this is my little bit of proof that this all is actually possible because we really did do it. So that's a bit of background. What I'm going to swing into now is 3 case studies, right? This is great to talk about it all in more of a theoretical sense, right? This is what we can do. But without sales talk, here is some actual results that have been made with NTop platform, some things that are really out there in the world. So this first one here is this United States Air Force CubeSat, right? This goes on a satellite. So the goal was to take this initial design right here on the leftmost image and lightweight this as much as possible. When you're launching things into space, that's quite expensive, so the lighter, the better. And in this case, what we were able to do is reduce the mass by 50% despite switching from aluminum over here to Inconel. And that's about a 2.5 times density increase. So this material is much, much heavier, but we still overall reduced the mass by about 50%. And because of that, we also increased the stiffness by 20%. But total, we reduced the weight by 2 pounds. And 2 pounds doesn't sound super impressive, right? It's only 2 pounds. But when you're launching things into space, every pound costs $20,000. So when you save 2 pounds per instance of this CubeSat, you can start saving a lot of money very quickly. In total, it only took 6 weeks from the time that they downloaded and the first time they first installed NTop platform to the time when this was completely flight qualified and ready to be put on that satellite. And this part is actually out in space orbiting somewhere. I don't know where, but it's out there somewhere. So this is a really cool part. The way we are able to do it is in these thin small beams here, we actually placed an extremely thin walled gyroid inside of there. Gyroids have a very good strength to weight ratio in terms of lattices, and they're very good in the compressive strength. So it has a lot of advantages, and it worked out extremely, extremely well for us here. The second case study here is one of my favorites. I think it's pretty interesting. This is a fuel-cooled oil cooler. Essentially, it is a 2-fluid flow heat exchanger. So take this image here on my left. Through this main chamber here comes our hot fluid. It exchanges heat and then goes out the top. And then our second fluid comes in this pipe on the left, exchanges the heat, and goes out to the right. And what we were trying to do is lightweight this part because this is for a helicopter, so every pound saved is a benefit, right? And also make this more efficient than the standard model. And we did that by using a gyroid, but a gyroid on a cylindrical coordinate system. We're one of the only, and maybe even the only, modeling tool where you can actually create a cylindrical gyroid. So we were able to take advantage with this implicit modeling of this extremely complex geometry to produce a design which increased the shared surface area by 146%. And with a 2-fluid flow heat exchanger, as the more shared surface area you have, the better performance you're going to get. And in total, to do all of this work where we did this structural ribbing, we rounded off all of these edges, we designed it for additive manufacturing so there's no bad overhangs or anything like that, it only took 2 days of design time, which is an incredibly fast turnaround. And thanks to all these added benefits that we did when designing it for AM, we increased the projected lifespan by 5 years because we reduced the amount of thermal fatigue this feels. So lots of really awesome advantages here. This was actually printed out on an EOS M290 machine. It was printed out of aluminum and aluminum alloy. So this is a nice light heat exchanger. And this third one I'm going to show you, this is just to talk about those reusable workflows that I mentioned before. So this is a medical device platter, right? We have some spinal cages in the back. We have some avascular cups up in the front. And what's going on here is this medical device company created a stochastic lattice. That's a lattice that allows for osseointegration, meaning your bone grows into the lattice so you have a much stronger connection. And they designed this process, this workflow inside of NTop platform that gets them to this really nice lattice. And they're testing out different variations on each of these parts here to find the best input parameters for that lattice to give them the best osseointegration. Now, typically in their normal tool, they would have had to redo every single step for every single part you see on this platter. And that took hours on hours of work. But when they used NTop to do this, they reduced their design time to create this platter by 90%. And that was a huge benefit, right? The less engineering time you have to put, well, the less direct hands-on engineer time you have to put into something, the cheaper that process gets. So these reusable workflows have a lot of potential advantages. I'm going to talk to you a bit more about them. All right, so those are my slides. I don't want to spend too long in the slides. I'm going to hop over into the actual software itself. But before I do that, what I'd say is don't forget this is a conversation as much as possible. So as I'm going through this, please put any questions you have in chat or feel free to just unmute and ask me a question. I'm happy to answer any of them at any point in time. So this is NTop platform, and I like to start off by saying this looks very similar to your traditional tool, right? Here where I have my geometry, this is our viewport. This is where we view our geometry, right? In the top here, this is our ribbon. So this is where all of your functions would normally be found in your traditional tool. But we work on a block-based system, so much like your functions, this is where all of our blocks are housed. And it's over here on the left where we really start to differ. The left side here, this is where you'd normally have your tree, and that's where you have step 1, step 2, step 3, all in sequential order in your normal tools. But in NTop platform, this is where all of your blocks are housed and essentially where your workflow is housed. So I said NTop platform works on a block-based system. What do I mean by that? Well, if I want to create a cube, I come up into my ribbon, I find that block, and I create it, and this new block over here gets created in my notebook. And if I'm going to do something like infill this with a gyroid, which is normally a fairly difficult task in your traditional tools, I go over to my new block, and it's how I nest these blocks together that I create and manipulate this geometry. All right, so I just created 1,000 unit cells of gyroid in a few milliseconds, right? And I can actually show you exactly how many milliseconds that took. It took exactly 32 milliseconds to make all of those gyroids. And then if I want to do something crazy by bumping this up by a gigantic factor and making 1,000,000 unit cells of gyroid, I can also just go ahead and do that. And it took almost no extra time. So this is my little implicit modeling, lets you do quite a lot of complex things very quickly and very easily. But why don't we back up just a bit and do something slightly more realistic than filling a cube with a gyroid, right? So let's take this brake pedal and let's design it for additive manufacturing. To do that, I want to infill this blue area that I just highlighted with a lattice. And not just any lattice in this case, I'm going to use a conformal lattice. That way I don't have any open beams or anything like that. To do that, since I have this imported CAD data, right, I'm starting from CAD, I can make use of it where I can select both the top and bottom faces, create a conformal UV mapping, and then I have to just type in the name of my new block, which is conformal lattice between CAD faces. And then I start filling out those needed inputs, and I start to get my first design iteration. Now this first one is not exactly conformal, right? We only have one cell division, but it just takes a small amount of effort to put more cell divisions and get my nice conformal lattice just that quickly. Now, like I said, reusable workflows, quick iterations, I can keep changing this up as much as I want until I find my favorite design iteration. So you can do these complex tasks very, very quickly. Now this lattice is great. It's a conformal lattice, so it has some added benefits. It's already been designed. That's great. But for NTop platform, it could tend to be a bit boring still, because these beams are all uniform thickness right now. And I mentioned earlier this idea where we can unify simulation and design. So if I switch over to a slightly different file, I ran a static analysis. So inside of NTop platform, we have several different types of simulation. We have static analysis, modal analysis, buckling, and thermal analyses already baked into the software. And I see a couple questions in the chat. I'll get to those in just a second. But I ran a static analysis on my brake pedal. So I held my back end fixed. I'm pushing down on the face of my brake pedal here. You can see my displacement. And what I need to do is make sure that this part doesn't break when I actually go to use it. Because if your brake pedal snapped in half, that's going to be a bad day when you're driving your car. Nobody wants that. So I'm actually physically able to reference these stress values. Where the stress is high, I can define a very specific beam thickness. Where the stress is low, I can define a thinner one. And what that ends up looking like is this here, where I have a nice thick beam where that stress was high, tapering down to the nice thin beam where that stress was low. And so that means I'm putting the strength where I need it and keeping or removing the weight where I can. So this is what I call a little bit of optimized lightweighting. Now, we designed this part, right? So that's great. You can design these things. The next step is to get these out of the software so you can print them. So how do we do that? Well, the traditional way for additive manufacturing is to turn this part into a mesh and export it as an STL. And in NTop platform, that is completely possible. I didn't do it because nobody really likes STL formats. Of course, you can export this as an STL or a 3MF. That's totally possible. But in NTop platform, we also have the ability to directly slice these parts inside of NTop platform. So we don't have to deal with an STL if we don't want to. And we can export these slices here as a few different formats: CLF, CLI, SSL, or black and white image stack. You can see we have a couple partner printers here. They make that transfer just that much easier. So this is just another way to get out of the platform that really can reduce the amount of headache you have to deal with if you're not working with an STL. So this is a really interesting pathway out of the software. Now, I have a couple questions in the chat, so before I move on, I'm going to get to these. Is it also possible to fill the cube with a honeycomb structure? Absolutely. We have several different types of honeycomb built into the software, so I'll just back up and show it to you guys, because that's not a very difficult task. I can do cube. I can fill up with a volume lattice here. And as I start nesting these together, I can come down here. We have different types of honeycombs: triangular, hexagonal. Pick hexagonal, fill type. And now my lattice is a honeycomb. And it's a little bit difficult to see here because it's infinitely thin, but we do have that honeycomb structure being made. So absolutely, you can do things like honeycombs as well. All right. So there's another question that came in. It said, I'm guessing there's tools to help you optimize the parameters being used. And I'm not quite sure what that question means. So if you could just give me a smidge more, I want to make sure I answer the question correctly.
Yeah, so one of the things you mentioned, I forget the exact terms, but it was basically referencing the number of crosses that you draw, and you can tune that during your design iterations when you're working out what side of mesh to use. Again, I'm sorry because I don't remember the exact terminology.
Yeah. So in that sense, right, how can I know which lattice to use and which beam thickness, right? That's kind of where that question is going.
Basically, yeah, and how many beams to use.
Exactly, right? So I think the answer there, which this is nobody's favorite answer, is that's still up to you, right? So NTop can do all these awesome things. We could take this design we have. The smart thing to do is to mesh this again and run it through another static analysis and get the maximum stresses and make sure it doesn't break, right? That's the smart thing to do. But is it going to directly tell you use this lattice with this many unit cell and this many divisions? Not directly, but because you can reuse these workflows, What would be possible is if you make a change to this lattice, it will rerun that entire static analysis automatically, so you can iterate through your designs as fast as possible to get that proper design. So it's not going to pick it for you, it's still up to you, but you can automate through, and it's just that much easier. So that's,
Okay.
yeah, that's a bit of a roundabout answer, but but that's we can't replace designers, at least not today. So thank you guys for asking the questions. They are great questions. Let's talk a little bit more about these reusable workflows and what they mean. So I have this initial CAD geometry. This is my impeller, and you can see I can select those faces and edges and all that sort of stuff. But what I need to do is shell it, infill it, join it all back together, and I'm even going to section cut it so we can look at it a little bit easier. But we want to do all these steps. And to shell this part, infill it with the gyroid, join that all back together, and section cut it, you can see all these steps on the left-hand side. Not very many, about 6. Nothing crazy going on. Looking at it in its totality might be a little scary, but trust me, it's about 2 minutes of work. But let's assume that I need to find the best shell thickness and combination with the best infill. And so that means I'm going to have 50 or 100 different iterations of this that I'm going to test, whether physically or through finite element analysis. Either way, what I really don't want to do is all of these steps on the left 50 to 100 times for every single new iteration. Don't want to do that. That's too much work. But with this reusable workflow idea in our implicit modeling, what I can do is come back to the very beginning of my workflow where I have this shell distance. And I can make a change. So I can make this shell twice as thick and change the infill type. And it's going to rerun every single subsequent step along the way and just give me my new design iteration. And this is possible because we're not working on working with face 17 and edge 42 on that face, right? We don't have those references. We're not subject to those same failures. So I can start from the very beginning. And let's take this a step further. If I want to take this workflow and apply it to any CAD body that I have, we're able to do that. And we're actually able to package it up as a custom block. So this whole workflow we created, we can save it, define the very specific inputs we want to be able to change. In this type, it's the fill type, the shell distance, and the CAD body. Package that whole thing up, go to a new instance of NTop platform, and you know what? Why don't we use this bracket? We can go here, type in the name of this custom block that I created, give it my bracket body, and it's going to go through all of those steps of that workflow again and give me my new design iteration. Even if I make some complex changes, and even with a completely different starting geometry, this workflow is reusable. Because we're not working with those boundary representations, we're working with implicit volumes, we can do these sorts of things very easily. And I see a fantastic question in chat that Liz did answer in the chat, but I always like to pull up my task manager. The question was, what kind of computer do you need to work with this? Well, biggest thing, you need to have a Windows computer. That's the biggest requirement. We don't have a Mac operating system yet. But one thing I'll say is, look how many NTop instances I have open at once, and I'm working on a laptop. So I have an i7. I have a lot of RAM, right? 64 gigabytes. That was an upgrade because I do a lot of finite element analysis. But it's not the world's most expensive laptop, and it's nothing special in terms of GPU either. It's a 4 gigabyte graphics card. So you don't need a supercomputer to do all of these things that I'm showing you live from my laptop. So that's some good information. Let's talk a little bit about topology optimization. This is probably my favorite topic total, right? I did 3 years of undergraduate research when I was obtaining my degree in mechanical engineering, specifically in additive manufacturing. Topology optimization was one of the things that I did a lot of work on, and it's my favorite. So topology optimization is going to take us to this nice, organic, optimized geometry. The question is, how do we get there, and how difficult is it compared to the legacy tools? Well, first off, we're going to start here with some initial imported CAD geometry. And this middle section here is what we're actually going to be optimizing. What we're going to be creating is an automotive structural bracket. But this blue chunk of material, in this case, is not my initial design. This time, it's my total design volume. So it's where my part can exist. Now, what that lets me do is use topology optimization to generate my initial design. So I'm doing some generative design in this case. Now, topology optimization, I'm going to assume you guys have some form of knowledge of it, but that's probably a bad assumption. So I'm gonna briefly touch on a couple things. What we need to do is turn our design space into a mesh. It's a finite element process, so we have to mesh this part, and we then have to go through the process and apply boundary conditions to this mesh. So we need to load it, how this part is going to be loaded. We can have multiple load cases. We can optimize it to, maximize the stiffness while reducing the mass. All of those sorts of things. All of the normal topology optimization stuff you can do here inside of NTop platform. But that's not the hard part. The hard part starts once you have this initial design. So you go through that process, you mesh it, you put all the boundary conditions on, you say, okay, optimize my geometry. You get this sort of result here, and this result has a couple issues. The biggest issue is the surface. Because it's computed from a mesh, it's tessellated everywhere, and it's very coarse. It has lots of stress concentrations. In short, it is entirely unusable. You can't use this as is. So we need to do some work. And in your legacy tool, this work's going to take you hours. It's going to give you an STL file. You're going to have to try and do mesh smoothing. That's in most tools, at least, but it's not a fun process. Trust me, I used to do it a lot. The second part is, maybe in our optimization process, we have some geometry here that's too thin, right? It's not connected to anything. It's not usable either. And normally, if you see this issue, you're going to have to rerun your entire topology optimization so that this will bump up. You're going to have to up your volume fraction, rerun a whole new top up. Not what you want to do. NTop platform gives you a little bit more access. So if you want to bump up to some elements that are maybe technically, according to the optimization, less necessary, you have total discrete control over this idea. So you can bump up that volume threshold, and now we need to, so we tackled the thin region area, now we need to tackle the surface. And in NTop platform, we have this button, not this button, this block here called smoothen body. So to smooth this entire body into something usable, it takes about this much effort in NTop platform. You use one block and it's done. So now that I've solved that problem, I have a smooth, usable geometry, no stress concentrations, no thin regions, all that sort of stuff. But we might notice that I smoothed away my connection regions. So that's a new problem that we've created here. But with implicit modeling, I grab those volumes out in 3D space here, those ones where I need the sharp corners and the sharp features, and I just do a basic Boolean operation back to my geometry. So now I have my nice sharp features with a smooth transition into my optimized geometry here. So what do you do now? We have our initial design. Well, what we do now is we mesh this part and we run a static analysis. So we go to our stress, we take a look, we make this picture a little bit prettier for you guys to look at so we can see where our stress is. And we can see here we have some high stress in some regions, we have a stress concentration back here, but we have low stress in others, right? Lots of things going on. But maybe we find out, in this case, we actually have a very high factor of safety, right? If we're going to be printing this part out of titanium, let's say, and maybe our max stress over here, 1.6 megapascals, that's not entirely concerning. That's not a lot for titanium. So we have some extra room to work with. What else can we do? Well, we can use this simulation data again, right? Unify simulation and design, and we can take it and we can shell this geometry. So we can shell this complex geometry. And not only that, we can shell it based off of that simulation data. So where that stress was high, we have a solid part. And then it tapers to where that stress was low. We have a nice thin wall. So again, we're putting the material and the strength where it's needed, and we're saving the material where it's not. So now we've done some variable shelling based off of some very precise simulation data. And that's a really, really great process here. All right. Now, the question comes is, okay, you shelled this part, and now I'm not sure how familiar you are with the different additive manufacturing processes, but if I were to print this out of a powder bed process, so I'm printing it out of titanium, that means there's a whole bed of powder. That means this entire cavity I created is going to be entirely filled with powder, meaning I would be not saving any weight if I don't depowder this part. So how can I take care of that issue? Well, what I can do in NTop is perforate to any body. So if we want to, what we're able to do is apply these perforations that we're looking at to any body in NTop platform. And what you'll notice as I'm panning around, zooming, rotating, all that stuff, these perforations are perfectly normal to the surface at every point. But not only that, as I'm moving away from different reference geometries, I am changing my spacing and my diameter. So I have complete control over these perforations that can be applied to any body. The reason I'm showing them to you on these headphones and not on my top-up part is because these perforations could be used for more than one thing. And as with anything in the NTop platform, there's more than one application for that block. So in this case, I'm perforating these maybe for lightweighting, maybe for aesthetics, maybe for acoustics, or maybe for the powder removal step. But there's a whole large amount of different ways that we can use these perforations here. Now, there's a couple questions in chat, and Liz is being fantastic in answering some, but I'm going to make sure we got all of them. So the question was, what method / algorithm is being used to generate the optimized geometry? That's a great question. I'm not going to dive into that today. That's a little bit too deep for this introduction. Essentially, it's a simp method. I'm going to leave it there, but nothing out of the ordinary. I think we have a paper about it somewhere on our website if you'd like to know more. Okay, so we've talked about a whole lot of different things. And what I want to switch over to is this example here where I have some stochastic lattice. Now, I mentioned these stochastic lattices in that case study earlier, right? They're typically found in the medical area where they're being used for implants and osseointegration. What I want to use them for is to show you a couple terms that I used is, reusable workflows. I'm not sure if I said the term unbreakable geometry, but that's something that we also say quite a lot. So we have these bars essentially of extremely complex lattice structures here. They're completely random and we have control. So if I want to change up my density, well, let's point out what's going on here. I'm changing up different things about these. So this bottom bar, what I'm doing is changing the density as I go from right to left. So I'm changing my cell size as I go from right to left. And on the top, what I'm doing is changing my beam thickness. So I'm going from a thin beam to a thick beam. Now, I have control over this. So on this lower bar, if I want to up my lower cell size, I can make those changes. If I want to make my upper cell size even larger, I can continuously iterate through these designs just like I was doing with more simple models, even with something as complex as these stochastic lattices. So you have a lot of freedom and a lot of control over something like this. But what I really, really like to show off here is up top with these beams that I'm changing the thickness on. If I were to make this upper thickness so thick that all of these beams are intersecting, right? So I would have like 100,000 or 200,000 intersecting faces, I'm not going to get an error. I'm able to go ahead and create this geometry because I'm not subject to those same failures because I don't have faces and edges and points. So this idea of complex and unbreakable geometry really is true with NTop platform. Now, is this design a good design? Right? Probably not. But you can look at it, you can make that decision, and you didn't get a failure, so you're not sure, oh, why did that fail? I'm not sure what's happening. You can just look at that and say, okay, I need something a little bit smaller than that, and just back yourself down. So you have a lot of freedom and a lot of complexity that you're able to work with here. Now, taking this idea here, let's take a look at this example. And this is not necessarily a car seat, but a racing seat. So what I have going on here is I'm using those same stochastic lattices for something different, and this is what we call architected materials. So what I'm doing is using these stochastic lattices on some form of polymer printer or something in that area, but I'm going to use these stochastics as my cushion. And in this headrest here, I mentioned that these stochastics are random, completely random, but that was a lie. We actually have control over just how random these lattices are. So in this case, you can see a lot of hexagons that are almost perfect, but some that are also distorted to make this more conformal nature. And maybe I find that this more ordered version gives me a nice stiffness property for something like a headrest. Maybe for something like the backrest, I really let this randomization go wild. So I have something more like a natural foam, like a natural sponge happening here. So maybe this gives me more of a cushion. I'm architecting it to be softer and more cushiony than the headrest. But we can also take all three of these ideas that I've been talking about and combine them. So now with my bottom seat here, I am putting a much denser foam where I'm sitting, so I have more support. Around the edges, it's much more sparse, so it's more cushion and it gives me that nice comfortable feel. But I'm also changing up the randomization. So I have some nice ordered ones, I have some very unordered ones, but we have complete control over these things when doing this sort of stuff. So lots of ways to use this lattice and control it and bend it to your will, essentially. I have two more topics, well, two more files that I'm going to talk to you about today, and this involves surface texturing. So I've been talking to you about latticing, topology optimization, lightweighting, and all that sort of stuff, but this is a topic that's been gaining more and more interest with a lot of our customers, is surface texturing. And what I'm showing you here is just this little rectangle, but what I'm doing is applying some different textures to the surface. And right now, I'm using a lattice to subtract away and create this cubic texture. Maybe this cubic texture has some really nice grip properties. Maybe this is for aesthetics only, right? That's either way you want to use it, that's totally fine. But because this is NTop platform, implicit modeling, and field-driven design, we can actually blend from that cubic structure on the outside into a more diamond structure in the middle. So now I'm blending from one texture to the other as space varies. Maybe this diamond texture I place where I need more grip, or maybe I use it to make something even more aesthetically pleasing. There's lots of different things you can do there. But we're not restricted to just using lattices to create textures. We can do things like adding surface roughness. So if we want to design a heat exchanger like I showed you earlier, something that's good to do is put surface roughness so that you can ensure that your flow is turbulent and therefore exchanging as much heat as possible. So we can apply surface roughness, we can do things like using those stochastics to create different things, embossing instead of subtracting, debossing, different types of noise, a whole lot of ways to do surface texturing. But we're not restricted to something as simple as this rectangle or as simple as these ordered textures either. We can do something even crazier. And in this file, what I did was took a donut, essentially, and I applied a faux wood grain texture. So this is a wood grain texture that I could apply to any complex body throughout 3D space, which is completely conformal, and I have complete control over it, right? So this is based off of a few equations that create this periodic texture out in 3D space, and I have inputs that make changes to it. So if I change up the period here, I'm going to get a new design iteration on my wood donut in this case, right? So here's my new design iteration. You can see it changed it up. And you can do these complex types of surface texturing just this easily, right? I'm still just changing up one basic thing. And so there's so many different ways you can use NTop platform, and that's what I was here to show you today. So this is the last file that I have prepared to talk to you about. We have 15 or so minutes. I would love to open it up to just open Q&A at this point. If you have questions, either put them in the chat or ask away. I'm going to look in the chat and see if there's any I missed that Liz didn't get to, but if you have any others, just ask away.
Evan, there is one from Kutan that
Okay.
I don't know. Yeah, maybe you can answer that one.
Yeah, so, okay, so I think it says here, can you integrate the manufacturing parameters specific to the process, SLM, EVM, into the optimization process? Depending on the powder and machine, input limits result in failed prints, thermal distortions, etc. So, does my topology optimization say, okay, I'm doing this for an SLM machine with these process parameters? No, it doesn't do that because we're not doing print process simulation at the same time. That's a very complex simulation that nobody directly incorporates into topology optimization, at least not today. What we can do is incorporate your knowledge of this process. So a couple of constraints that are coming out is going to be minimum feature size and overhang constraints. So okay, I'm printing this out of aluminum on my EOS M290. I know I can have a 30-degree overhang, but the minimum feature size I can have is 200 micron. So you're going to be able to incorporate those types of constraints directly into your optimization, but not just click, concept laser and just have it do it for you, right? You still have to know what you're doing for the optimization to be able to run. So kind of a yes and no, but what I can say is more of that is in the works right now. Okay. So question coming in here. For the example with the wood grain donut, is it possible to convert to CAD and simply click on surfaces to modify one specific grain line? So no, it's not, right? This is an implicit model. In this case, I don't have any CAD in this file at all. In some cases, you can convert things back to CAD, but this is not something you want to convert to CAD geometry. This would create hundreds of thousands or millions of CAD faces to attempt to recreate just how complex this is. You can see I have roughness and things like that. That's not something that CAD's going to be able to handle. And that's why we come to NTop platform, right? We want to do these complex things that our CAD tools cannot do. So by rights, we're not going to convert this back to CAD geometry because your CAD tools cannot handle it. And we don't have a lot of those functionalities. So can I click on one little line and pull the grain and that sort of stuff? No. But these different inputs or parameters, right, I can make a change to them, and maybe that's going to solve my issue. But in this case, you're not going to be able to just pull and drag a polyline to suit your needs, not directly at least. Not the way I created this file. All right. So this is a question I haven't actually had before. This is an interesting one. I'm curious about the legal implications of the software. If a user implements the optimized topology that NTop gives, but finds that the part breaks, is NTop legally responsible for the failure? And what I'm going to say is absolutely not. They should have tested that before they put it on the car, right? Something like, so if your design engineer designs a part and then it breaks, it never comes back to the software, at least what I've seen in the legal world. It always goes back to those design engineers because they have that professional engineering license. It is their job to make sure their design is safe for use. So is it the design software's fault? No, because we could have made it usable, but they just didn't do their due diligence. What I would say is it's up to that design engineer to make sure they do enough simulations and verifications of their geometry. But that is the first time I've got that question, and an absolutely excellent question. All right, one question from a little bit earlier is what new features are currently being developed? And what I'll point you to here, I'm not sure if you all have access to this, but if you do end up getting access to it, if you go to File, Settings, there's this little option here for Show Beta Blocks. And if we show these beta blocks, up in my ribbon, I get a new tab. So there's a lot of new ways of creating lattices coming out. We're what we call our lattice pipeline. We're creating a new foundation for how they're created. Not to take away any features. Actually, all of those current features are incorporated in these blocks, but to give you more complex abilities. So doing things like extremely conformal complex latticing, creating your own unit cells, and still being able to do it fast and easy. Different analysis exchange types, simulations for volume meshing. So many different things are in the works that I can't give you a list because there's too many. There's too many. What I will say is we update our software every 2 weeks. So if I click on this little question mark, I go to what's new, it opens up the documentation for what's been added. This was this 2 weeks update. We did a complete UI overhaul. We also put new properties, new types of blocks, documentation, slice layer types, and I can keep paging through. You can see how many things get added to this software every 2 weeks. So I physically can't give you a list because it's too big. But we update very often, and we pack it full of really useful, really interesting updates. All right, so question was, is it possible to perform stress and thermal analysis such as FEA using the honeycomb structure? Absolutely. So that honeycomb structure that I created, which is probably still back here somewhere, probably didn't get rid of it. I did get rid of it, so that's on me. But absolutely, right? You would need to give it some thickness. Then you'd have to do your meshing and do your normal stress and thermal analyses. That's still possible with any type of lattice. Just it's possible with any geometry that you create in NTop platform. One thing I'll say is you don't have to do your stress analysis or thermal analysis inside of NTop platform. Our solver is for linear steady state analyses. That means if you have very large deformations or anything non-linear in that sense, what you'll need to do is take your volumetric mesh, and let me back up a bit. So if we have this volume mesh and we want to take it to do a more complex simulation, we can actually export it to Abacus, ANSYS, Nastran, LS-DYNA, or universal format, so we can get it into pretty much any other complex solver that you need to do. So if you want to do CFD to verify your heat exchanger, you can get this part to that solver that you need. And then you can bring that data back into NTop platform, just like the stress data in here. We're able to bring that external data back into NTop and use it again to modify your geometry in the exact same way. So we can handshake that data with those other solvers very, very well. All right. So great question here was about the business side of things. Are NTop models used more often for research purposes and virtual simulations, or more for industrial manufacturing? Does NTop have a focus on what kind of industry needs they'd like to meet? I don't know if I have that slide on my presentation. What I'll say is NTop serves mainly, I think not mainly, but our four biggest industries are aerospace and defense, automotive, industrial, and consumer products. So from everything from rocket ships to iPhone cases, NTop has a hand in, including medical devices like spinal implants and all that sort of stuff. We have a gigantic amount of, we have a very large amount of customers in all those different areas. But we also have a very large EDU presence now, and it's just gaining steam. Liz is doing an incredible job getting us out to do these sort of research projects. So we have a lot of research going on as well. So your answer to your question is yes, essentially, to all of that. We have a large stake in a lot of different places. The question was, when I demoed the topology optimization to minimize my stress concentrations, how much user input was there for that step? Why don't I just back up and show it to you? So this smooth and body step has a grid size, a smooth iteration, and an interpolation type. 3 inputs it took me to get to this nice, smooth, usable geometry. 3 inputs. So you need to find the right values here, but it doesn't take a lot of work or a lot of time. It's a very, very easy thing to go ahead and do. So not a lot of user input at all. All right, so this is a slightly different question, but a fair one nonetheless. Are there roles in our company for mechanical engineers? What skills are you looking for in applicants? What I'll say is, I don't know about the rest of the company who they're looking for necessarily, but the application engineering team, my team, I'm a mechanical engineer. I think all of my other coworkers are also mechanical engineers. Everybody comes in with their own subset of speciality. I came in with topology optimization, simulation, and automation. We have some people that are really good at the consumer products, so aesthetic designing. We have a PhD who did his PhD in lattice structures, so he's really fantastic at that sort of stuff. There's not one single subset of skills that our company needs, but I'm sure we have open positions if you want to check out our website and see what fits for you. I don't know what's open right now. It's not my job to know or to care necessarily, but we're adding a lot of people right now, so feel free to take a look. All right. Well, it seems like the questions are kind of tapering out here. What I will say is, thank you guys for letting me talk today. I know I rambled on for about an hour here, but I had a blast talking to you and answering your questions. Liz, have we pointed them to the EDU Slack by chance?
I thought I did, but I can do that as well. If they do apply for a license, I'll send them lots of resources to get up and running. So that won't be a problem. Here, let me put the Slack in there. So we do have an EDU Slack workspace where lots of people answer and ask questions. It's a great place to get inspiration too. That is now in there.
Awesome. Thank you.
Great. I guess there is no many more questions. So Yvonne, thank you very much. Excellent talk. I enjoyed every second of it. I'm sure a student did, and I can see from their question, their excitement, and I'm sure next lecture they're going to bombard me with many more questions. So we hoping to have this software. In fact, like the UBC purchased the software so everybody can have access. This year was a little bit late, and beside the this COVID situation, because everybody is at home, then it was a different story. But I will be in touch with you guys. But great, thank you very much, Liz and Ivan. I know it's late in New York, but excellent job. It's great. Again, it was late in summer when Liz first sent this email about the NTop. First, I thought, okay, another CAD software. And then I checked here and there a few videos, and then I was excited too, similar to students. Now that I'm learning more about it, I'm even more excited. So thank you very much, guys. Great. So
Thank you.
You guys want to say anything else to the students, or any final comment?
I just, again, I'd say thank you for having us. It's always fun for me to come talk to you guys, get new questions every time. So if you have any more questions, you want to learn more, again, reach out to Liz. She'll get you a license and we'll get you up and running. The more people we have using NTop, the happier we are, even though it's free for you guys. So it's not just about the money in this case.
All right. Have a good rest of your evening.
Thank you very much, everybody. Great.
All right.
Thank you very much. Good night.
Bye, everyone.